Welcome back, everyone. This is video 2 for chapter 7. We are going to discuss chemical sedimentary rocks today. Chemical sedimentary rocks form by precipitation out of water, and this can occur in two different ways: by inorganic processes such as evaporation or chemical activity, or by organic processes due to water-dwelling organisms, in which case you get a biochemical sedimentary rock. Examples of chemical sedimentary rocks include limestone, chert, and rock salt. Let's start with the chemical sedimentary rock limestone. It is the most abundant chemical sedimentary rock, composed of calcium carbonate, usually calcite, and can form either by inorganic or biochemical processes. Limestone has economic value. It is used as crushed stone in the construction industry, for example. Let's start with the biochemical limestone. These form from the shells of marine organisms, and a lot of marine limestone are formed from corals. Corals are organisms that secrete calcium carbonate skeletons and create coral reefs. Another biochemical limestone is coquina, which are small pieces of broken shells and or algae that is loosely cemented together. And finally, chalk. So here's our coquina. Here's chalk. You may not realize is composed from the remains of an organism called a coccolithophorid. And the skeletons of coccolithophorids are calcite. Here's a scenario of how coquina would form. We have broken up shells along a shoreline. They get loosely cemented together. This is an image on the left side of Australia's Great Barrier Reef, extending for 2,600 kilometers and consists of more than 2,900 individual reefs. As far as location of the reef, up here in the northeast portion of Australia. This on the right side is an ancient fossilized reef that is Permian in age, and the economic importance is it provides a reservoir for oil and natural gas. The holes where the corals lived in are now void, and as a result, oil and gas will migrate and sit in those openings. I mentioned chalk is made up of microorganisms. Here's a close-up view. This is a pinhead to show you how small these little organisms are. And they are coccolithophorids. You need a high-powered microscope to view them. This view here is the very famous white chalk cliffs of Dover, England. In the ocean, the coccolithophorids die in massive amounts and accumulate, and through the lithification process turn into chalk. Not all limestone forms by biochemical processes. Let's look at inorganic limestones. Travertine is an inorganic limestone that forms in caves. Oolitic limestone is composed of these small grains called ooids that get cemented together. Oolitic limestone forms in calcium carbonate rich waters, supersaturated in fact, and the ooids are tumbled in this calcium carbonate rich water, and layer after layer of calcium carbonate gets coated, and so you have these small little seeds. So the interpretation for the oolitic limestone is high energy environment, calcium carbonate, saturated waters. Here's travertine. in a cave. We have calcite crystals forming in a drop of water at the tip of what we call a soda straw, stalactite. And the crystals form as a result of carbon dioxide escaping from the water droplet. This is oolitic limestone. These are the individual ooids. There are other chemical sedimentary rocks besides limestone. Dolostone is related to limestone. It has magnesium along with calcium and bicarbonate. Chert is composed of microcrystalline quartz, very, very small grains of quartz. Examples of different varieties of chert include flint, jasper, and agates. Flint is in the first picture. It is dark in color because organics are present in this type of chert. Jasper is red in color. Here is an arrowhead that's made out of chert, and petrified wood is chert as well. Another group of chemical sedimentary rocks are referred to as evaporites. They form when an ocean evaporates and concentrates ions such as sodium and chlorine, which subsequently precipitate out as rock salt. Another example of an evaporite is gypsum. In some coastal areas, seawater is used to flood the land, and the water slowly evaporates away, precipitating out salt. So they call this salt farming. They are now excavating the salt and going to process it and sell it. Some of you may be familiar with the Bonneville Salt Flats in Utah. The Bonneville Salt Flats exist as a remnant of the Great Salt Lake. This lake used to be much larger and was called Lake Bonneville, and through time has evaporated down to its current size. The salt in this area can be 2 meters thick. Our last group of sedimentary rocks we'll discuss are organic sedimentary rocks, and we're going to put coal in this group. Coal forms from the breakdown of plant material, and the environment needed is a low oxygen, swampy environment. We can look at stages of coal formation. First, the breakdown and accumulation of plant material. With deeper burial, higher temperatures, greater pressures, that plant material will become peat and then a light brown soft coal called lignite. Upon further burial and higher temperatures and pressures, the lignite turns into bituminous coal, which is primarily what we burn here in North America. And if it is even deeper in the earth, it becomes a metamorphic type of coal called anthracite coal. Here's a visual. We have our swampy environment where peat forms. Upon deeper burial and compaction, we get lignite, then bituminous, and then finally the hard black coal containing the highest heat content is anthracite coal. I want to talk about how the sediment becomes a sedimentary rock. The overall term used is called diagenesis. That's all of the chemical, physical, biological changes that take place after the sediments have been deposited. Diagenesis occurs in the upper few kilometers of the Earth's crust. Some of the changes that occur after sediment has been deposited: lithification. Lithification includes compaction, and cementation. Compaction is exactly what it says. As sediments get deposited, additional sediments are placed on top, and that process continues until the weight of the overlying material compresses the material. Cementation involves crystallization of minerals among the individual sediment grains. It is the gluing together of the sediment, such as sand grains. Here we're looking at some clay-sized material that is loosely packed. There's water filling the pore spaces. As that material gets buried, because of compaction, you can see that the rock becomes more dense, the pore space decreases. Below is a picture of water circulating through individual sand or gravel-sized particles and precipitating out of cement to hold those grains together. I'm going to stop at this point. So this concludes video 2 for Chapter 7 on sedimentary rocks.